Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Sibusiso Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, good people, we are now looking at finance. It's a continuation of last week's lesson. However, today we'll be focusing on the grade 12 part of financial maths, that would be annuities. Remember, grade 11 finance is also examinable together with grade 12 finance. Good people, it's important to note that we are not just doing this topic or covering this topic because it's part of the curriculum, but there should be practical lessons that are learned from looking at this topic. We should be able to, in future, you guys should be able to make sound financial decisions using your knowledge of financial mathematics, and you should also be in a position of assisting your parents to make sound financial decisions, because in the world of finance, it's important that we make sound financial decisions so that we don't get to waste money unnecessarily. So we want to maximize whatever money that we have, and in order to do that, we need to be capacitated with skills of understanding how to use money and how our money grows, and even how we can save money when we are paying off loans. It can be car loans, it can be home loans, and so on. We should know how to work with that. We should also know how to maximize our money if we are trying to save money for the future. So this topic gives you those strategies and that invaluable knowledge that would enable you to be able to make good financial decisions. Right. Now, by the end of this lesson, obviously, you should be able to understand the meaning of the concept annuity, and you should be able to understand the meaning of the future value annuity. What does it mean when someone says the annuity is future valued? Should also know how to perform calculations using the future value formula. And you should also understand the meaning of the present value annuity and also be able to carry calculations out that involve present value annuities. Right, obviously you can refer to the CAPS document on page 42 and the exam guideline that was published in 2021 on page 6, just to check the scope within which you have to operate when you do your financial maths. Right, the knowledge that you come in with to this lesson that would be crucial would be your geometric series, would be your simple interest, compound interest, linear and reducing balance depreciation methods, nominal and effective rates, and timelines. If you check here, I indicated that they are very, very important. You would recall from last week's lesson, we were using a lot of timelines to solve these problems. We are going to do the same today, because it makes work very, very easy. So it makes your work organized, and you are able to then perform calculations in a structured way. Right. The background. Now, in grade 11, we learned how to deal with individual payments and withdrawals separately and to perform calculations. What if the same amount, we're dealing with individual payments and withdrawals, different payments and withdrawals? What if the same amount is used, or the same withdrawal is performed at regular intervals over a long period of time? You are paying off a car, you pay the same amount at regular intervals over a certain period of time. You are saving money, you investing money, you invest a specific amount over a certain period of time, the same amount at regular intervals, say end of the month, you deposit the same amount. So you are then talking about now you are talking about an annuity. Now we have an example. A parent is saving for his child's university fees by investing 1,500 monthly for 10 years. So you can see that it's this amount, constant amount, that is invested. And the interval here is monthly, because we are saying same payment, that is 1,500. We are saying regular intervals, and the intervals are monthly in this case. Now another one, a house is bought and the payment for the house is 6,500 monthly for 20 years. You can see here monthly talks to your intervals, and then same amount, 6,500. So when we are talking about that, we are then talking about something new, which is called an annuity. Right. Now let's continue with the background. Given the two examples above, there are special formulae that should be used to accommodate these payments in one single calculation. These formulae are known as the annuity formulae. So we are going to use annuity formulae to be able to perform those calculations using a single formula. Now in grade 12, we cover two types of annuities. That is the future value annuity and the present value annuity. Future value used to save money for the future when you invest. Present value annuity, when you borrow money from the bank and you have to pay it off, then that money is then referred to, or the type of annuity that governs that amount would be referred to as the present value annuity. Right. Understanding annuity, let's define so that you understand what an annuity is. An annuity is a series. You remember geometric series, arithmetic series. When you take terms and you add them, then you call that a series. Now, of equal payments, so the terms there are equal, made at regular intervals for a certain amount of time. An annuity is subject to an interest rate, good people. There's an interest rate that the annuity is subjected to. Examples of annuities involve regular savings, retirement annuities, home loan repayments, vehicle loan repayments, etc. The formula you will be using in grade 12 is based on the following assumptions. So this formula, for these formulae to work, you are subjected to these assumptions. All payments are equal. The payments are made at regular intervals. The interest remains fixed. Very important. The compounding period of interest is the same as the payment intervals. What does this mean? It means that if it's compounded monthly, then the payments should be made monthly. If it's compounded quarterly, then the payments should be made quarterly. Which means that if there is a difference between the two, then you have to convert the effective rate or whatever rate that you have to a rate that is compounded the same way in which the payments are made. If payments are made semi-annually every after 6 months, then your interest should also be semi-annually. If it's not, it should be converted to that. Otherwise, the formula will not work. Now, the final payment is made at the time that the total accumulated amount is calculated. Now, what happens is these formulae work to the last payment. Even if you are withdrawing money, the assumption is that that particular month you pay and then you withdraw, because our formula works to the last payment. Wherever the withdrawal is made, there should be a payment that is made, or the accumulated amount is calculated to include the last payment. It works to the last payment. You'll see as we start to work with this. Right. Now let's begin with the future value annuity. Remember, we said we have a present value annuity and we have a future value annuity. Now we begin with the future value annuity. The future value of an annuity is the total capital, including interest, that accumulates by depositing equal regular payments. Very important. You deposit equal regular payments into a savings or an investment account. So future value, you are saving money for the future. You are saving money for the future, so you are then using a future value annuity. So now what happens is that X now represents the payments that you are making, and the gaps here represent what? The intervals, to say it's monthly or it's yearly or it's semi-annually, whatever. The gaps in between these payments should be equal, and they represent what? They represent the regularity of the payments there, or the intervals there. Now, if you check here, for this formula to work, the last payment should also be made where F is calculated. Where F is calculated, the last payment is made. And also, there should be what? An interest rate. There should be an interest rate that is constant and does not change. And remember, we said the interest rate should be the same as the compounding periods, right? We can use the following formula to calculate the future value. There is the formula now. This formula is derived from a geometric sequence. It is derived from a geometric series. So you can derive this formula from a geometric series. You can check it out in your books, the derivation thereof, but it is not examinable. And the formula is in the formula sheet. That's very, very important. You'll be given the formula in the formula sheet. Now let's explain each parameter in that formula. We have F as the future value. We have X as the equal and regular payments per period. You have N as the number of payments. Very, very important, good people. We are now moving away from N being the number of years or the time in which the amount stays in the account. It's different now. N represents the number of payments that are made. Very, very important. It has nothing to do with, because it's coming from R there. So we know that I is equals to R divided by 100. That is the fractional interest rate. Now, the future value formula is used whenever payments, small amounts, are made first and the total large amount is accumulated and collected later in future, and future value. Right, we use the future value when we work with retirement annuities. You are saving money for when you retire. Savings account, you are saving money for your child's education, or you want to take a holiday trip, you save money for that. And also in sinking funds. Sinking funds are used in the world of business, where companies try to save money so that they can be able to replace machinery in future. Let's say, for an example, in farming, they are using tractors. We know that these tractors would have a shelf life. Maybe they have a lifespan of 10, 15 years. After 10 to 15 years, then the company intends to replace them. Then the company tries to save the money now so that the money can be used in 15 years' time. Such accounts are known as the sinking funds. Right. Now, future value annuity. Now, let's look at the example. Let's look at how we can apply the future value annuity. Mr. Shongwe, which is myself, opens a saving account for his son's future education. We start planning now for the future, right? He deposits the amount of 600 at the end of each month. You see, the amount is deposited at the end of each month. So you can see that the payments are made monthly, and we are expecting the compounding to also be monthly. Now, for a period of 10 years, the interest rate is 12% per annum, compounded monthly. You can see here that you are paying each month, the interest is compounded monthly. That's very nice. That's what we said is expected for us to have the formula to work. Calculate how much Mr. Shongwe would have accumulated at the end of 10 years. So we want to know how much I would have in my son's account by the end of 10 years when he goes to tertiary. It might be tertiary education or high school. Right. Now, let us look at the solution. Remember, good people, I said timelines are of paramount importance. So we are going to be using timelines in every problem that we are going to be solving today. Right, now you can see I've brought in the timeline. T0, that is when the investment was made, the account was opened. At T1, after the end of the first month, I deposit 600. T2, end of the second month, I deposit 600. Now, we are going to check in 20 years how many months are there. So we multiplied 10 by 12. We got that we have 120 months in 10 years because we are paying monthly. So our timeline intervals should be monthly. And then now it continues also with your T3. T3 also here. T3, the amount is still the same, 600, and so on and so forth to T119, T120, but you can see the amount that is paid there is the same. The amount is the same. And now I've converted this. Remember I said I is equals to R divided by 100. So I've converted the 12% to 12 over 100, which is 0.12. And then it is divided by 12. Remember last week you did compoundings. So the 12 there means that in a year we are going to compound 12 times because we have 12 months in a year, because we are saying compounded monthly, hence the division by 12 there when it comes to the interest rate or the fractional interest rate. Right, because we are saving money for the future, we have to use the future value formula. There it is, as in the formula sheet. So this is the future value formula. X will then represent the equal and regular payments. I is the fractional interest rate, and N is the number of payments, and then I again the fractional interest rate there. Now let us substitute and see. Now after substituting, you can see where there was X, it's 600 now. Where there is I put in the interest rate, 0.12 over 12. And then now the number of payments, I'm going to show you how to calculate the number of payments. If you start from T1 until T120, it would mean that you would have made 120 payments. I'll show you how to determine those. You are going to take now top minus bottom plus 1. So you are going to take the upper interval, subtract the lower interval. That would be your 120, subtract 1 where we started, and then plus 1. So that is how we calculate the number of payments using our timelines. So that's how we got 120, because there are 120 payments made in 10 years if it's made monthly. So now you can see the accumulated amount is 138,023 there. Right, and 21 cents as well. So now you can see this amount. I was just saving 600. It has accumulated to 138,000 in 10 years. You can also be able to calculate the interest here. If you are to take the number of payments of 600 to say 20 multiplied by 600, you will know how much you've paid to the bank. 20 multiplied by 600, that gives you times 12, because you are actually paying monthly. So it's 10 years, 12, and then you are making 120 payments of 600 rand. So it's 120 payments of 600. That gives you, what do you have here? 72,000. So the amount that you've paid from your pocket is 72,000, but you get 138,000 out. So you can be able to calculate the difference between the two in order for you to get the interest that you got from saving that money. Right, we are moving on, but I need to show you here. Note the number of payments are determined by taking 120 minus 1, the last payment, minus the first payment plus 1. Right. We move on to example 2. Suppose that at the beginning of the month, 2,000 is deposited into the bank at the beginning of the month. At the end of the same month, a further 2,000 is made. So you can see if it was in January, beginning of the month, there's money that is paid. Also, end of the month, there's money that is paid. So there are 2 payments made in January. Now, and a further 2,000 at the end of each month for 5 years. So at the end of each month now, we are paying 2,000 as well for 5 years. The interest rate is 6% per annum compounded monthly. So we are actually making monthly deposit end of each month, and we are compounding monthly. So we are okay. How much money would have been saved in 5 years? It's still future value. You want to know how much you'd have in future if you start saving. Now, let's see. Again, there's a timeline that comes through here. You can see this amount should be here. It should be here at T0. T0, this 2,000 should be here at 20. There's a mistake there. Now, you can see that because there was a payment that was made at the beginning of each month, now we have a payment at T0. As opposed to the previous problem here, if you look at this one, there was no amount that was made that was paid at T0 because there was no immediate amount that was paid. So, but here, when you check this problem here, you can see that there's an amount, there's an immediate amount that is paid because at the beginning of the month we make a payment and also at the end of the month. So at T0 we have a payment, right? Now from there, you can see that now if you are to calculate the number of payments, you'll take the period here for the last payment and here 60 minus 0 plus 1. So you can see that in total you'd have made 61 payments because there is an additional payment that was made there or an extra payment that was made before the annuity started, because the annuity starts here. Remember, annuity in this case would be at the end of each month. So end of each month, end of each month, end of each month, we are making those payments, but there was a payment that was made at the beginning of the month, so it's an extra payment. Right, let's see now. Obviously, we are saving for the future value annuity. We substitute X with 2,000, and then we have the interest rate is 6%, 6 divided by 100, and the 12 for compounding monthly. And then, most importantly, the number of payments are 61 because we've made an additional payment there. And then from there, if you are to calculate, you're going to get 142,237 rand and 76 cents there as the future value that accumulates. So you can see that this money grows. It grows exponentially because of compound interest, because of the interest that it accumulates. So it's interest built on top of interest. Right. Let's move on. Okay, right. Obviously, this I've already explained. To determine the number of payments, 60 minus 0 plus 1. So we got that it's 61 payments that were made there. All right. Variations in the future value annuity formula. The formula as you see it can have some variations. If they try to then confuse you by making payments different to how the annuity should be looking like, then you should be able to cope with such. Now, what are those variations? Same amount is being invested in equal intervals for a certain period, but instead of being withdrawn, it is left in the account for more time without making any further payments. I'll give an example. I'm saving money for my child's future education, and I expect him to be in grade 12 in 10 years' time. And then it happens that in between, he repeats some grades. Maybe he repeats grade 7, and then he also repeats grade 10. So I've subjected the money, or I'll be paying monthly, I'll be making monthly deposits of 500 per month for 10 years, because I'm expecting him to be done by at the end of 10 years. Now, at the end of 10 years is not done. So I leave the amount. I say, okay, I'm no longer going to make additional payments into the account, but I'm not withdrawing the money because my son is not a tertiary for now. So what am I going to do now? I'm going to say, okay, I instruct my financial institution to say, leave the money for me. Just leave the money for me until he finishes. You find that he finishes 2 years later. So that money, because it was in that account and there was no more payments that was made, but the money continues to gain interest there. So those are some of the variations there. Now, amount greater than or less than the annuity is paid into the account. Let's say you start by paying 5,000, and then from there you pay 1,000 every month. So you see, the 5,000 is not part and parcel of the annuity, because we said annuity should be equal and regular payment. So you get that now. It's 5,000 that is paid, and then after a month, then 1,000, 1,000, 1,000. So the annuity would start with those 1,000. Right. The same amount is being invested in equal intervals for the second period, but no payment is made at the end. Right? Equal intervals, monthly, quarterly, monthly, not variation, it's different compounding periods. So it's very, very important here that these are different compounding periods. So it can also happen that you have different compounding periods to what? To the intervals in which the money is being paid. Now, the above variations will be explained. Let us try to explain them. Same amount is invested for a certain period, but instead of being withdrawn, it is left in the account for some more time without making any further payments. I'll use a timeline to explain this quickly. Suppose that you start making a payment at T1. Maybe I was actually depositing 500, T1, T2, 500, T3, 500. I do that, and then let's say I am doing it for 10 years. So this would be T120, because there are 120 months in 10 years. So I'll be at T120 here. I'll be paying 500. T119, I'll be paying 500. But instead of withdrawing the money here, I leave the money in the account for a further 2 years. That would be 24 months. So that would then take me to T144, because I'm leaving the money for a further 2 years without making any other payments here. So which means that here I'm no longer making the payments, but I'm leaving the amount to grow further, because this is subjected to an interest rate, say, of 10%, which means that now the annuity would be here, where I am making the payments of 500 rands annuity. The annuity would be there. So, but this money continues to grow. The money continues to grow until T144. So how am I going to deal with that as far as the formula is concerned? I am not going to perform the whole calculation. I'm just going to show you how to can actually analyze that and how to infuse that variation in the formula. So we know that we have our future value annuity to govern this annuity here. And the future value annuity is given by x into 1 plus I to the n minus 1 over I. This is the amount. This is the future value here. But you can see the future value continues to grow. So it continues to gain interest, even though no payments are made, which means that the annuity stops. Our annuity stops at 120. So we have that our annuity stops. It stops at 120. But the amount continues to grow. Because the amount continues to grow, we are going to add that interest. We say 1 plus I, that is the compound interest, but then it continues for 24 further months. 1 plus I raise 24. So that is how you are going to vary the formula. So to calculate the amount, the total accumulated amount, you can see that we've taken the future value, and the future value has actually earned an interest. So that is how we are going to be dealing with this variation. Remember, this N here stands for the number of payments, but this N here represents the duration with which this amount stayed further in the account. So that is the first variation. Right. Let's move on quickly to the second one. Amount greater than or less than the annuity amount is paid into the account. I'll make an example here. Suppose that you have an amount at T0. The amount is, say, 1,000. And then T1, you now start paying 500. T2, you start paying 500. T3, you start paying 500, and so on and so forth. Let's say you do it for 5 years, so that is 5 times 12. You are paying it monthly, that is 60 months. So T60, you also pay here 500. So T59, 500. So if you check this amount, the first amount that was made there, that was paid there, it is not part of the annuity because it's different from these annuity values. So it's a different amount. It's not part of the annuity because it's different from the annuity amounts there. So we can see that here the annuity is here. This is our annuity. Our annuity here. So this is not part of the annuity, not part of the annuity. So how do we deal with that? How do we deal with that? How do we calculate the accumulated amount? How do we calculate the accumulated amount? So what we need to do here is, because this amount stays in the account for a specific period of time, we should be saying, let us add the accumulated amount. Let us add this accumulated amount to what? To our future value. So we're going to grow this amount separately, and then we are going to add that to what? To the amount that we gained from the annuity. So if we grow that by compound interest, just like you were doing in last week's lesson, just like you were doing in grade 11, you will see that this would be 1,000 rands into 1 plus the fractional interest rate. And then how long does it stay? It stays there for 60 months. Remember, in the compound interest formula, N represents what? The duration with which the amount stayed in the account. So, but we need to add to this because this grows on its own here. But then we need to add what? The annuity. So we are going to add x into 1 plus I to the n minus 1 over I. So that's what happens here. That is the second variation. So you are going to grow this amount using compound interest, but then when you start here, you have annuity. So you're going to grow the next amount using the annuity. Right, same amount is invested, in equal intervals for a certain period, but no payment is made at the end. Now let's show that in a timeline. Let's say we are also doing this, say, for 4 years, 4 times 12, and we are doing it monthly, 4 years, and we are compounding monthly. So let's say we start at T1, we make a payment of 300. At T2, we make a payment of 300 at the end of the month. And then because it's for 4 years, it's T48, and then T47, T46. So this would be 300 as well, 300 as well. But now it says no payment is made at the end. So instead of making this payment here, there is no payment here. Remember, I said in the formula, for us to be able to calculate the future value there, we should make a payment. If we want to calculate the future value up till the 48th month, the assumption is that there is a payment that is made in the 48th month. That is the assumption for this formula to work. But if you check here, there is no payment that was made at the end. There is no payment that was made at the end. So now, in order for us to get our future value, we need to be smart about this, because we are going to calculate now the accumulated amount here now should be equals to, it would be, we will take those that are part of the annuity. Remember now, the annuity stops there. So we'll take those that are part of the annuity, and then we'll say that represents what? The future value, like that. But then we are also seeing that this amount is taken here, so we are going to grow. So this would be our future value 1. In order for us to calculate this one, we grow that by 1 month. So multiply by 1 plus I to the 1. So we grow that further by a month, because for the formula to work, it stops here where the last payment was made. So, but for us to get what is at T48, we need to grow that by a further 1 month, like that. Right, we are moving on. This is an activity that you have to do. I am going to give you just 5 minutes, good people, to work on this activity. Just 5 minutes. Please make sure that you work with this as quickly as you can, so that we can be able to proceed to present value annuities. 5 minutes, and your time starts now. Hello and welcome back. I hope you were able to solve this Tabo problem. Let's see. Tabo wants to save up money to buy a car cash. Wants to buy it cash after obtaining his degree from university. He opens a saving account and immediately deposits 500. So there's an immediate payment at T0. After this, he continues to deposit 500 at the end of each month for 4 years. So it starts immediately, and then from there at the end of each month for 4 years. The interest rate stays fixed at 8% per annum, compounded monthly. So we are happy he's paying monthly. The compoundings are monthly. At the end of 4 years, Tabo does not withdraw the amount and leaves the amount for a further 2 years while completing his honors degree. So he decides to do his honors degree and he says, no, let me not withdraw the money. I'll buy the car when I have my honors degree and I'm ready for the workplace. Now calculate the total amount accumulated after 6 years. So you can see that this is a problem that is part of the variations that we just looked at. Right. Solution. Let's see now. Obviously, I told you timelines are key here. Timelines are key here. Now, if you check here at T0, because there was an immediate payment, immediate, this is the immediate payment. So this would be the immediate payment there. So this would be the immediate payment that was made at T0. And then from there continues at the end of the month, end of until T48. So there's an amount that is paid at T48. Remember I said that for the formula to work, the last payment should be made where the money is going to be withdrawn. So our future value is at T48. But instead of withdrawing it, Tabo leaves the money to grow for a further 2 years, and 2 years is 24 months. So 48 plus 24, that gives us 72 months. So the whole investment period is 74 months. So now, in order for us to calculate the future value, we have our future value annuity formula. You can see the amount is calculated using what? The future value that we get here multiplied by, because the money, this future value continues to grow. Remember, this money continues to grow for 2 years. So we are growing that money for a further 24 months. That is why this is the interest. We are adding, we add interest to that money, because we are no longer compound, or we are no longer making those annuity payments, but the money stays in the account, so it gains interest for a further 2 years. So that is why we have the N1 here, which represents what? Number of payments. And then we have the N2 here, which represents what? The duration of the period with which the money stays there. Now we start. If we check, the number of payments here would be 48 minus 0 plus 1. 48 minus 0 plus 1. That is N, the number of payments. So we have 49 payments. That is why this is 49, because there was an immediate payment. We know the amount there is 500. We know the fractional interest rate, but this money continues to grow for a further 24 months. So we are going to have that, we are going to add interest for 2 years. That is the added interest for 2 years, because this amount, the future value, remember this is our future value, it continues to grow because it's still in the account there. Now the amount that we get here is 33,852 rands and 82 cents. So that is the future value of that particular investment, right? Now, let us now move or shift focus to the present value. Remember, future value, you save money for the future. Remember, good people, you should be able to know. One of the most important skills here would be to know which formula to use. So if you save money for the future, you use the future value annuity formula. Fine. And then if you take your loan, you borrow money from the bank, you use the present value annuity. There can be another variation on the present value where now a lump sum of money is put into the bank, and then the bank gives you money monthly, so you take from that amount. So it works like a reverse loan, as if you borrowed the bank the money, now the bank is paying you back the money. So it's a reverse loan. That one you should also be wary of, right? A present value of an annuity refers to paying back a loan by equal monthly installments. Paying back the loan by equal monthly installments. Interest is calculated using compound interest, compounded monthly, quarterly, and so on. We also refer to the present value annuity as a reducing balance loan, because as you pay, the money that you owe reduces. So it's a reducing balance loan. Right. No, note that. That's very, very important. The present value involves two types of loans. The first loan is where someone borrows money from the bank and repays the loan with interest. That is the first part of loan. The other involves a loan where a large sum of money is invested in a financial institution, and the financial institution pays back the investor equal monthly amounts over a certain period. Let's say, for an example, you inherit from your grandfather's estate, you inherit, say, 10 million, and you don't want the whole amount at once. So you invest it in a bank. You say, now, let me give this bank or the financial institution this large amount, and you expect them to give you the amount monthly, to give you back certain amounts. They pay you back monthly. So it's like a reverse loan. So you are the one who borrowed them the money, then they are paying you back. So that's how it works there. So now what is also important here is that there is a 1 period gap. You can see it's very, very important, the 1 period gap. So you take a loan here, that is the loan taken there, and then you start paying off like that. So that is one, also it's a type of an annuity. Right. Let's look at the formula. Now if you check, formula looks similar to the future value annuity, but instead of FV we use PV, and instead of having 1 plus, because with the future value we have that this is x into 1 plus I to the n minus 1 over I, but here you can see it's no longer 1, it's no longer this minus 1, it's 1 minus, and the n now is negative n, and then from there divide by the fractional interest rate. The formula is in the formula sheet. You don't need to memorize the formula. It is there in the formula sheet. It's available for your use. Now, P is the present value, X is equal and regular payments, N is the number of payments, I is the fractional interest rate. Now, NP, very, very important here. There must be a 1 period gap between when the loan is taken and the first payment for the formula to work, which means that if you are going to pay off the loan monthly. The assumption here is that you cannot borrow money now and start paying now. Can't, otherwise it means you did not need the money. So the assumption is that there should be a 1 period gap. You borrow money now and then you start paying back the money a month later if you are compounding monthly. But if you are compounding quarterly, you borrow the money now and then you start paying after 3 months. If you are compounding semi-annually, you borrow the money now, you start paying after 6 months. You see, so we are using the different compounding periods. So that is why we are saying there should be a 1 period gap. If you are compounding monthly, there should be a 1 month gap between when the loan was granted and when the first payment is made. You can see it from here. This is the gap that we are talking about here. This is the gap that we are talking about. The loan is granted here, but the payment is made after a 1 period interval like that. Right. Now, when do we use the formula? We use the formula for the repayments of home loans. Times with some of your parents, they are still paying off the home loans. We also paying out of the vehicle loans. When they have a car and they've taken the car on finance, still paying it off. Student loans. Some of your brothers and sisters are at tertiary and your parents had to take a student loan, so they are still repaying those loans. So you can see here we are talking about loans there. That is the present value annuity. They give you money now at present and then you need to repay the money. So it's a present value annuity rather than saving money and taking it out at the end. That is the future value. So you need to be able to differentiate between the two. Right. Now we go straight to an example here. Kulego wants to buy a house and takes out a loan of 1 million. He repays the loan over 25 years. So it takes 25 years for Nkululeko to settle the loan. The interest on Nkululeko's loan is 8.5% per annum compounded monthly. So the compounding is monthly. Determine the monthly repayments. Compounding is monthly, Nkululeko pays monthly. So we are sorted. Assume that the first payment starts 1 month after drawing of the loan. So you see, this is the 1 period gap that we are talking about. The 1 period gap that we are talking about. So now we say calculate the total amount of money required to repay the loan. Calculate the total amount of money required. So we need X, the annuity. What is the annuity there? Calculate the total amount of money required to repay the loan. So we need to know how much Nkululeko was paying first. That is what monthly. You need to know how much you should pay monthly and then we proceed from there. Now we've set up a timeline. As I indicated, all the problems that I'll be solving here, I'll be using a timeline. So we've set up a timeline. 1 million is taken here. After then a payment is made, another one will be made here. So we make those payments. This is the gap now. The gap now. There should be a 1 period gap between the period, the time when the loan is taken and the first payment. Right. Now, present value annuity formula, that is the formula we use. So now, how many amounts should we make here? N should be 300 minus 1 plus 1. 300 minus 1 plus 1, like that. So we get that this is 300 payments. Nkululeko will make 300 payments. Right, that is why here we have minus 300. This is the loan amount. So monthly, Nkululeko should be paying 8,052 rands 27 cents. This is the monthly payments or monthly repayment that Nkululeko should be making. Right. Now let's check. The total amount required to repay the loan. Now, if you check, remember we said Nkululeko would make 300 payments. So you can see if he's paying 8,052 rand 27 cents, 300 times, then he's going to get 2,415,681 rands and 25 cents. So you can see that he borrowed 1 million, but he's going to pay 2.4 million. So you can see how much more you are paying because of what? The interest that this amount accumulates over a period of time. So for interest sake, let's look at how much the bank gained. Interest that the bank gained from the client is 1.4 million. So the interest, it is found to be way greater than, it's almost 2 times, 1.5 times greater than the amount that he originally borrowed. So these are things that you are subjected with when you make those home loans. So you guys should be able to find ways and mechanisms to be able to negate this interest here. So in future, as you grow up, you buy cars, you buy houses, you should be wary of these type of interest that is paid, and you should find ways to negate the interest. How can we negate it? Can negate it by making extra payments or by just slightly increasing the amount of money that we pay per month. By just slightly increasing it, we can actually make sure that some of the interest there diminishes. So that is why I said to you, it's important when you look at this section, you're not only looking at it now as being part of the curriculum or the syllabus, but you also look at it for the future. When you grow up and you start making financial decisions, you should make informed financial decisions using the tools that were given to you when you did your financial maths. Right. Now, let's look at another example. Musa borrows 500,000 from a bank and repays the loan by equal monthly payments of 8,000, starting 1 month. You see, we start 1 month after granting of the loan. This is our gap. Interest is fixed at 18% per annum compounded monthly. How many payments of 8,000 would be made? How many payments of 8,000 would be made? Right, let's see now. Obviously, I said to you, timeline. Good people, please familiarize yourselves with using timelines. They are going to become very handy in order to for you to organize the information and be able to carry out those calculations. Now you can see this 500,000 is borrowed there. The amounts of 8,000 are made until the period X, because we don't know how many payments have been made, so we want to calculate the number of payments made. Let's see. It is a present value annuity because we're talking about borrowing, so it's a loan. Let's check here. Now the unknown is N, because they say how many payments should be made. The unknown is N. Now, good people, we know if it's exponential like that, then we should be making use of what? Logarithms, because this is N is an exponent there. So to be able to calculate, to bring this down, we need to use the laws of logarithms that you've studied when you were doing your functions, because with functions you were able to move from an exponential graph to a log graph. So we use the same knowledge there. Right, now converting this to log form, the log of a number, the number is this, and then that's the base, and then we are going to solve for that. Obviously, what you do is you can multiply there. You have that this is 500,000 multiplied by 0.18 in 12, and then you divide everything by 8,000, and then which means that this side will be left with 1 minus 1 plus 0.18 over 12 to the negative n. And then from there, you are going to then transpose the 1. So you will be able to get 1 minus the whole thing here. If you take this side here and you take it that side and this one this side, so you are going to have 1 minus. So 1 minus, there is the 1 minus part, and then when you introduce a log, you are going to get that. We are just using the laws of logs, good people. Right, so now we get that n is equals to 186.22. So this tells you there are 186 payments of 8,000. And then this 0.22 is telling you that there is an additional payment. There's an additional payment that is less than 8,000. Let's see here. So 187 payments of 8,000 were made. 187 payments were made in total, because this is 186.22. So you'll be making 187 payments, but it's 186 payments of 8,000. These are full payments, 186 full payments. And one payment less than what? 8,000. Full payment of what? Of 8,000. And we have one payment less than 8,000. Later on, I'll be showing you how to calculate this payment. I'll show you later on how to calculate this payment, the last payment that was made, which is less than 8,000. Right. Deferred annuities. Let's talk to deferred annuities. When the first payment of a loan is made more than one period after the loan was received, we refer to the payment of the annuity as the deferred annuity. Remember, we said there should be a 1 period gap. Sometimes the gap becomes bigger than 1 period. So when the gap is now bigger than 1 period, let's say for an example, the loan is granted here. Instead of making the first payment here, the first payment is made there. Instead of making the first payment at T1, the first payment is made at T5. So we refer to this, because there should be a 1 period gap, we refer to this as the deferred annuity. So I need to show you how to work with the deferred annuity. Note that the present value of annuity will still be located 1 period before the first payment. We will apply compound interest to the loan to move it to the same point on the timeline as the present value of the annuity, which means that we have to then say this is the first payment, we leave the gap, this would be the gap there, so we grow the loan to there. We grow the loan to 1 gap before the payment is made. So that is what we have to do there. Now let's look at an example that governs that. Simpua takes out a 20-year loan of 100,000. She repays the loan by means of equal monthly payments starting 3 months after granting of the loan. The interest is 18% per annum compounded monthly. The interest is compounded monthly. Calculate the monthly repayments. Now, if you check, instead of Simpua paying, because it's making the payments monthly, instead of paying the first month end, Simpua pays 3 months later. So you see this 1 period gap here is no longer what you call accounted for in this case, because there are 3 months there. So we are not conforming to what the formula wants, because the formula wants a 1 period gap. In this case, because we're working with months, it's a 1 month gap. Now, let's see how we can work with that. Look at what happens now. Instead of the payment being made here, because the loan is granted here, this is our PV. Instead of the payment being made here, the payment starts being made after 3 months at T3. So what should we do? We should, from the first payment, we leave a gap. So we should grow this PV here, PV2. If this was PV1, we should grow this present value to there. and then from there we can be able to calculate. So this loan should accumulate 2 months worth of interest for us to be able to then use the formula effectively. So you see, this is the present value annuity. Now you see, now this loan amount has accumulated interest. This is the interest that it accumulates, and then from there we can be able to calculate. Now let's see. It's 100,000. It gains interest for 2 months, because remember we should use a 1 period gap. So because of that, the money grows for 2 months first. Then we are now conforming with our future value annuity. Then we can calculate number of payments. 240 minus what? 3. It would be 240 minus 3, because it's 240 minus that plus 1. So we get that it is 238 payments. And then when you put everything into a calculator and simplify that, you cross that and you divide it with this part here, we get that x should be 1,591 and 35 cents. So this is the money that should be paid per month. So this is how you work with that deferred annuity. Right, the outstanding balance. Now, outstanding balance, you are busy paying off the loan. Maybe you want to settle it. After some time, maybe you win a lotto and you want to settle the loan. So you want to know how much you still owe. So we call that the outstanding balance. The outstanding balance on a loan at a given interval or given moment is the amount that has to be paid to settle the loan. 2 methods can be used to calculate the outstanding balance. The first method is you take the loan, you grow it by certain certain interest over a given period, and then you take away, you subtract whatever that you have paid. So you are going to say, if I took this loan now, it would be in future, it would cost me this much because it has accumulated interest, and then you subtract whatever amount that you've paid. So the outstanding balance is loan with interest to date minus the repayments with interest to date. So you take the loan with interest to date minus the repayments because you are paying now for the future, so the repayments would be governed by the future value annuity. So we have that BN would be equals to a loan with interest minus F, the accumulated amount with interest. Why are we using the future value? Because you are going to pay in future, so this money now accumulates to pay off in future. So alternatively, you can use the present value of the remaining payments. If you know how many payments remain, then you will know the total amount that you should pay. To say, if I'm left with 5 payments, then I would know that I have to pay 5 times, including interest, then I'll be able to calculate the outstanding amount. So we are saying now we use the present value of the remaining payments. Now let's see how that would work in an actual problem. Nkululeko buys the house and takes out a loan of 1.2 million. He repays the loan over 20 years by means of equal monthly payments of 11,580 and 26 cents, starting 1 month after granting of the loan. So this annuity is not deferred because 1 month after the payment is made. So there is that 1 period gap. The interest on the loan is 10% per annum, compounded monthly. Calculate the outstanding balance on the loan after the payment was made at the end of the 5th year. Now, let's see our timeline coming in here. We are borrowing 1.2 million. We are paying off, I made a mistake here, it should be 11,580,26. So these amounts should be this one. Should be this amount, not the 11,000. It's a mistake on my timeline. So now we want to calculate the outstanding balance at the end of the 5th year. How do you work out the 60? You said it's 12 compoundings, or 12 you are going to pay 12 times a year times 5 years, so that gives you 60. We'll be able to work out the outstanding balance after 60 payments have been made. Now let's see. Using method 1, remember method 1, we said the balance would be A minus F. The loan, including interest. So you take the loan, you grow it. No, not here, until where you want to calculate the outstanding balance. You grow the loan for 60 months, and then you subtract whatever that you've paid for 60 months. So let's see. That is 1.2 million. It's a loan for 60 months. We take away the interest, or we take away the payments that have been made. You see, loan plus interest, and then we take away what? The payments plus interest. So this gives us an outstanding amount of 1,776,029.29 as well. So now we have that this would be our outstanding balance using method 1. We can also use method 2. Let's see. Method 2, same thing here. Bring in the timeline. Remember I said these amounts should be this one, not the 11,000. Now let's see. Now you see, now you are going to use the number of payments remaining. So you see here, how are you going to calculate the number of payments remaining? You are going to say, I've made 60 payments. In total, I should be making 240 payments. So it would be 240 minus 60 plus 1. So these are the number of payments that remain. So you see now, you are no longer calculating, it should be just 240 minus 60 there, which gives us 180. Let me check. Yes, it gives us 180. So it's 180 payments that remain. So now, because we have 180 payments remaining, we are going to use N as negative 180, because in this formula, to calculate the outstanding balance, we use the present value. You can see it's a present value annuity formula, but for the remaining payments. If you check that one, it gives you the same amount. The only thing is just a few decimal points there that are not correlating, but the rest of the answer is the same. So the answers are more or less the same, right? That is the outstanding balance. Now let's move on to the last payment. I think this should be the last part of our lesson, the last payments. When the payment amount is fixed beforehand, it is usually not possible to settle the loan by integer amount of payments. In such cases, there will be a last payment smaller than others to settle the loan. I think we've already spoken about that. So this payment is made one period after the last full payment is made. So if you check, last payment would be the outstanding balance, and then you grow it with 1 month. So it's the outstanding balance after the last full payment, and then you add 1 month interest. So this is interest. So we grow the outstanding amount after the last full payment by 1 month to get the last payment. So we can use two methods. I'll quickly take you through that. Anele borrows 500,000 from a bank and repays the loan by means of equal monthly payments of 8,000, starting 1 month after granting of the loan. That is the gap taken care of. Interest is fixed at 18% per annum, compounded monthly. How many payments of 8,000 will be made, and what would be the last payment? I think we've already calculated these in the previous slides where we were calculating the number of payments. We did get 100. It's the same problem. We did get 186,22, where I said to you it's 186 payments of 8,000 rands and one payment less than 8,000 rands. One payment less than 8,000 rands. So now we know we have 186 full payments and one payment less than that. So now let's see, 187 payments were made, 186 payments of 8,000 and one payment less than 8,000. Right, let's calculate that last payment. See, the timeline comes in. Now, to calculate that last payment, let's see. We see we've calculated the outstanding balance after 186 full payments were made. And then what are we going to do to the outstanding balance? We grow it by 1 month. That is why we have that 1 month. So did we add 1 month interest to what? To the outstanding balance after the full payments were made. Remember, outstanding balance can be calculated. This is the outstanding balance. It can be calculated using two formulas, which means that now, let's see quickly, we have 1,787 as the last payment. You see, it's less than 8,000. Alternatively, you can also use the method of what? The present value of the remaining payment. So you calculate the outstanding balance using what? The present value of the remaining payments. But now remember here, if you use this present value, you don't need to round off. No rounding off. No rounding off of n. So you don't round off n, you take all those decimal points for you to be able to calculate the last payment, and the last payment will exactly be the same as the payment that has already been calculated using method 1, because this is method 2. Right, good people, we've run out of time. I think we did justice to the concept of annuity. We worked with future value annuity. We also worked with the present value annuity. So the onus is on you to go back and try to answer as many questions on this concept as possible so that you'll be able to cope with the examination. Right, our lessons continue next week. We are going to be starting statistics. So please make sure that you also tune in next week for that. For now, it's thank you very much. Please take care of yourselves, take care of each other, and practice mathematics. Goodbye.